Lesson 9.4, Algebraic Representation of Transformations. Lesson 9.4, Algebraic Representations of Transformations. Example 1, Algebraic Representations of Translations. The rules shown in the table describe how coordinates change when a figure is translated up, down, right, and left on the coordinate plane. Translations. Write A units. Add A to the x coordinates, xy. So xy becomes x plus A, comma, y. Left A units. Subtract A from the x coordinate. xy becomes x minus A, y. Up B units. Add B to the y coordinate. xy becomes x, y plus b. Down B units. Subtract b from the x coordinate. xy becomes x, y minus b. They made an error here. Down B units should be subtract b from the y coordinate. Subtract b from the y coordinate. So xy becomes x, y minus b. They made a small error there.
Okay, so, we can take a look at the coordinate plane and we can look at objects or geometric figures in the coordinate plane and we can move them around. And that's called transforming them. Taking a shape and doing something with it and moving it or having it exist somewhere else, some other configuration. Let's take a look at some examples where we can actually be very precise about different types of transformations. Here's one. Let's start with this triangle here, triangle XYZ. You can see it here in the coordinate plane. And our mission is to graph the translation of this triangle 4 units right and 2 units down. Now, what does that mean? It means that we take this figure just as it is, and we're going to move it 4 units to the right and then 2 units down. Okay? This is a translation. We're translating it. So we can actually see this visually by actually putting a movable congruent triangle right there on top of it. So there it is. And now I'm just going to follow the rules. 4 units right. So what does that mean? It means I go 1, 2, 3, 4 units to the right. And then I go 2 units down. 1, 2. And that's the translated version of X, Y, Z. And actually what I like to do is I like to call these things, quite often we call them, I'm going to use a blue pen, X prime, which is just X with a little attitude. Whoop. Y prime. Whoop. And Z prime. Whoop. And so you can see that this corresponds to the Z. This vertex corresponds to the x, and so forth. And if you actually want to find the coordinates, of course, we could read the coordinates off, right? You could see what they are, right? For x prime, oops, I keep moving it, sorry. For x prime, I see it's 1, 2. For y prime, I see it's 3, -2, and so forth. But we could actually just use the rules and the original picture to actually figure that out. And I want to share that with you just really fast right now. Because you see what I could do here is take the coordinates of each point, which you can find. For example, what's the coordinates of x? Well, I go 1, 2, 3 units over in the left direction, so that's going to be -3, and then 4 up. Y is going to be -1, and then 0, because I'm staying on the x-axis, I don't go up or down. And then z is going to be -4, 0. And now the rule is to do what? Well, since I'm moving 4 units over to the right, that means that what I do is, in all the x values, what I do is I add 4. That's a positive direction, so I add 4. But then simultaneously, I'm supposed to move it down 2, which means I'm going to now subtract 2 from the y's. And so if you follow that rule, what we'll see here is that the x goes to a point which I'm calling x prime. And what do I do there? I take the x coordinate, and now I add 4. That moves it 4 units over to the right. And then I take the y coordinate, and I subtract 2 because that moves it down 2 units. And when you actually work through this, what we see here is 1. So I see that x prime is 1, comma, and 4 minus 2 is 2. And that's what we got. You see, 1, comma, 2. That's the x prime. It checks. And now you can do this for each of them. It's the same rule. For y prime, the corresponding vertex for y, I take the x, negative 1, and I add 4. Everything, the x's are being moved over to the right 4. And then with the y's, I'm going to subtract 2. And so here I see y prime is 3, comma, negative 2. Exactly what we have here. 3, 1, 2, 3, negative 2, 2 down. And then finally here with the z, it goes to z prime. And what I see here is negative 4, I add 4 to the right, and then in the y I subtract the 2, and so I see z prime is 0, negative 2, so that's going to be 0 moving this way, but 2 down, and that's exactly where we are here. So now you can really see this, and by the way, this notation just means that this is the coordinate that's associated with the z prime, for example, and so forth throughout. So you can see it really did go over 4 and down 2. Very cool. We, in fact, did a translation.
Okay, you may recognize this example from an earlier lesson, but the main thing they want you to recognize in this particular lesson is how to write the pairs using algebraic notation, which is like right here. That x prime, y prime, z prime, using the algebraic notation to describe what's taking place. Example 2, algebraic representation of reflections. The signs of the coordinates of a figure change when a figure is reflected across the x and y axis. The table shows the rules for changing the signs of the coordinates after a reflection. Reflection. Across the x-axis, multiply each y-coordinate by negative 1. So xy becomes x negative y. Across the y-axis, multiply each x-coordinate by a negative 1. So xy becomes negative xy. Okay, now remember, a transformation is a change in the figure's position or size. Translations, rotations, and reflections are types of transformation. A reflection flips a figure across a line to create a mirror image.
All right, let's take a look at another transformation. This one is a reflection. So the question is to graph the reflection of the triangle XYZ across the y-axis. So what does that mean? It means that I want us to think about what this object looked like if you were to kind of move it over the y-axis, like a reflection. In fact, imagine a mirror right there. In fact, you don't have to imagine a mirror. Oh, look at me. Okay, anyway, it's another story. But if you imagine the mirror right here, okay, and I'll just tilt it so you can see it now, because you don't have a good view. What you'll see is how it would look. And that's what it would look like. You see how it's a reflection? So it really, when you think of reflection, think mirror. And you really got it. And reflection over, across the y-axis means the mirror is going to be right on the y-axis, and then you see where it is. Okay, I don't know. You think that's, which is nicer, that look, or this look? Okay, anyway, separate question. All right, so how can you visualize this? Well, you could actually imagine doing it for real. Think of putting a movable triangle here on a sheet of paper or plastic, and imagine this, the binding of the book be right on the y-axis, and you're literally going to just turn the page. So turn the page, that's a reflection. Turn the page, that's the mirror reflection. And there it is. So how do you find that? Well, if you think about it, the y values aren't going to change at all. The height of this point, x, is not going to change when I look at its corresponding point, which I'm going to call, of course, x prime. And the height of the z and the y aren't changing as well. But what changes with respect to the x? Well, in fact, notice that by reflecting it, all we're going to do is have a sign flip. The sign will change, which basically means don't change the magnitude of the number, just change its sign. And so that's how we change the x values. That's how we change the x values. And let me show you what I mean. Oh, by the way, Did you fall for the thing that I think you might have fallen for? Is that really y prime? I don't think so. Because when we reflect the page, that's the z. Gets way over there. That's the z. Now, why would you let me make that mistake? This should be z. Because this corresponds to the z. And when you flip this, this corresponds to the y. This is a classic mistake, which I did deliberately to see if you were following. So there's the y prime, there's the z prime, and I'm sticking with the x prime. Okay, so, but back to what I was saying. So the heights don't change, but the x values have to change sign, which means multiply by -1. That's what it means. So multiply by -1. So that's the rule. So if I come back to the actual rule here, I can find the coordinates for x prime by doing what? Just by multiplying the x value by -1 and do nothing to the y value. And so what's this? Well, then x prime is going to be -1 times -3 is going to be 3, and then comma 4. Let's check it. 1, 2, 3, 1, 2, 3, 4. What about y prime? Same rule again. I multiply the x by -1, do nothing with respect to the y value, so y prime is going to be 1, 0. Now check this out. 1, 0, where is it? That's going to be 1, 0 is right there. So if I wouldn't have caught that mistake a moment ago, I would have caught it right now. Because the rule tells me that that has to be a y prime, and of course we see that is the reflection. So even if you make a mistake sometimes, you might catch your mistake even a little bit later down the road. So that's awesome. So congratulations to you. And z prime, same thing. -1 times the -4, and 0 we do nothing with. That's going to be a z prime of 4, 0, which knows exactly is, again, the z prime. So there you have it. We've actually seen a transformation that's of the reflection type, where you actually have to be reflective.